After too many expletives. Righto. So, who's got specific questions they want sort of addressed? I did send out an offer for people to send in questions, but nobody did. So I wasn't even sure whether people had got the message from Blackboard to know they could come today. Righto, who's got what? Who's got questions they don't know how to do, or they want to know how to explain from sort of any of the stuff that we've done essentially?
I believe it might be question 1 on that practice exam.
Yeah.
Going back through the notes, I had B. And my notes say D, 2 significant figures.
Yeah, it's because of the way. I don't particularly like these sorts of questions. I don't mind having significant figure questions like the second one, where you're expected to do a calculation. So you multiply 2 numbers together, and you think, okay, so how many figures can I quote my answer to? Then it makes sense. But when they just ask you a straight up, let's work out if you remember the rule we told you for significant figures. Normally they say that, like, if it's zeros after the decimal point, then they're significant. Yeah, and for that reason, yeah, like.
But they have to be after the point, but before
the end.
Like,
yeah. But like you say, you could write 0.0086 as 8.6 by 10 to the negative 3, right? And think, well, now it's only got 2 significant figures. Yeah. But like I said, it's a sort of a textbook definition of it rather than anything of much practical importance. The main thing I expect people to do from a significant figures point of view is, if you start off with a number from a laboratory or a calculation and you've got 3 digits and you're asked to multiply by another number that's maybe got 3 digits, then your answer is 3 digits. Doesn't matter how many digits the calculator might express it to. And it will happen a little bit with multiplication, but it happens more so with division, where you measure something and it's 10 seconds and you say, well, that was 3 periods. That was 3 oscillations, so the period was 3.3 seconds, right? And you think, okay, well, I can probably live with that because it started at 10. But when you write 3.333, I start saying these are ridiculous. Just record the number that makes sense. Yeah. But yeah, there are some questions there where you sort of think, I don't think that's really, what we're trying to teach you in this thing. The textbook definition, just that you need to be sensible about how many figures you quote. Yeah.
Did you write this semester exam?
Yeah.
Did you write the last one?
First semester of this year, yeah. So I've written a paper which is sort of, because past exam papers were written by somebody else, I've tried not to just sort of go at right angles to the existing papers, because otherwise people think, but it looks nothing like the practice exam. Yeah. But because we do the in-class questions along the way and more conceptual questions and less sort of straight out, if you guess the formula you're okay type questions, it's happening, it's morphing, but it's morphing sort of slow enough rather than just bang, here we are, this is a completely different paper. Good luck, guys. Yeah.
This might be a stupid question as well, but do we have access to more than just that exam?
No, well, between the practice exam and the like you get another 5 lots of questions, 5 questions for each of the 5 modules on the way through. Yeah. Yeah, you get an idea of the sort of questions and the content. Yeah. I mean, it is one of those things where it's writing. Part of the reason is writing completely new papers every time. It's just too time consuming, and often you have questions that you sort of think, oh, this is a pretty good question that drills into the concept we want you to understand here. So let's use that question. But once it sort of gets used too many times, it's out in solutions and stuff like that, people just remember the answer rather than appreciate why the answer is what the answer is. Yeah.
I'm guessing that's why you haven't given it last semester.
Yeah, some of the questions on the in-class questions that we did this time around will have come from there almost. So that it's one of those things where the ones that come up in the in-class activities, sort of, yeah, you sort of think, okay, let's try this question, see if it works, and if it doesn't work, you sort of think, right, I can't use that on the exam paper because there's some aspect of that question that just doesn't resonate with them, so they don't understand what we're asking. So let's not put that on the exam paper. Yeah. So most of them sort of go through a little bit of that. Try it here, and it's not so much damage if it's in a, you know, you do 5 module tests, and then when you do the maths, one question's probably worth less than 1%, and you think, okay, nobody got that right. That's not that question either needs to be reworded or let's not use it again. Yeah.
And you said that module 1's going to have most.
Yeah, the other thing that you can take for sure from this thing is the breakdown of the paper is the same, because module 1 is generally the longest module in the lecture thing and has more questions than the rest of the things. So it's something like 10, and then the other 5 modules have got about 5 or 6 or 7 rather, depending on where you're at, to get to 44. Yeah. So the numbers of questions for each of the modules is pretty much the same as the existing papers. Yeah.
Question 10.
On here?
Yeah.
Okay.
I have to do like 3 or 4 times.
Yeah, this is probably like as close as you get to a sort of a traditional physics question, if you like. And there's 2 concepts being sort of tested, if you like, or 2-dimensional version of the question. So essentially, yeah, you have to resolve the tensions into the vertical and horizontal components. Okay, so if you the tensions aren't drawn on here. So what we're sort of drawing over here effectively is almost like if we wanted to draw a proper free body diagram over here, you'd sort of draw something that looked more like here's the mass. I know the weight's in that direction, and there's a piece of string pulling that way and a piece of string pulling that way. And the only way it can stay where it is if the vertical components balance each other, then it won't move in the vertical. And if the horizontal components balance each other, then it doesn't move in the horizontal either. So it should stay where it is. Yeah. So that's effectively what you do here. You sort of say, we've chosen it in a symmetric notation so that you're told that this angle here and this angle here are both 37 degrees. And that makes it relatively easy then, because the horizontal components cancelling requires the 2 tensions to be the same. So this, whatever that tension is and whatever that tension is, they have to be the same magnitude so the 2 horizontal components cancel. Okay, so then you say, what's the vertical component of this tension in that direction? Okay, so when I draw the tension in that direction, it's really indicating the direction that the string applies a force to the mass. So the string is pulling the mass up, the mass is pulling the string down. Yeah, but from this mass's point of view, weight is pulling it down and the 2 strings are pulling it up. Yeah, so that's what that diagram's about. So then you say, okay, so if that's the direction of the T, then the bit upwards is T times the cos of this angle. Okay, but that's T times the sine of this angle. Doesn't really matter how you do it. So you either do it with 37 and say, if that's T and this is the, from that angle's perspective, the opposite side of the triangle, then it would be T sine 37. Or you can say, oh, but hang on, if I use this angle down here, it would be T, and it would be adjacent and hypotenuse, so it would be T cos of that angle, but it would be the cos of the angle down here, the 53. Okay, so you either work out the composite angle and do that way. Okay, so that's what the 2 sort of expressions down below are saying. No, they're not. Oh, the horizontal bit is, yeah. Okay. But yeah, that's about as, detail the question, because there's a couple of stages to getting to the solution. And, it's probably one of the things that you could easily understand people sort of thinking, oh, it's a bit of a rip-off when these questions are multiple choice questions, because you might understand how to do this question and do 80% of it right, and do something wrong right at the end and get the wrong answer. Whereas somebody else might just recognise the question and say, oh, it's this answer, I don't know how to do it, but I know it's this answer. Yeah. So that's essentially why we do the sort of mix of multiple choice and short answer questions on the way through, so people do get a chance to sort of, display that they can solve, questions in a, proper logical problem solving fashion. Here's my diagram, here are the conceptual bits, here's the equations, here's my algebra, here's the answer.
Why do they take them out of the exam?
Originally that was the case, and my preference longer term would be for us to go back to something which is some sort of hybrid of the two. Yeah. Because there was a time when we did sort of have ludicrously large class numbers, sort of 300 or so, and then you start thinking, if they sit that exam late in the exam period and I have to get all of it marked and get it into the system by blah, that's not going to happen. But yeah, my view would be that I would prefer us to have a combination of multiple choice and short answer questions longer term. Yeah. But there's no easy answer. It's just how it evolved, and it hasn't sort of shaken out of its current configuration yet. So you will see questions on this paper as well that we sort of think, well, hang on, we didn't do that. So that would be the case with this question here, because we didn't really do uniform circular motion and centripetal force terms. Okay, so from time to time you might see a question on this paper and think, well, I don't remember us doing that stuff, and there is some stuff on rotational motion that we didn't do.
So in terms of our exam, if we didn't look at it a lot, or if it was kept to a minimum in our lectures and stuff, No. If we haven't sort of done it in the lectures, it's not going to be covered in the paper. Sort of was.
Oh, very, very vaguely. Yeah. No, if we wanted you to understand how centripetal forces work and that sort of thing, we do it in a bit more detail than that. Yeah.
Can you go through question 40 in the exam?
40. 40, yeah, okay. Okay, so that's this question down here.
Yeah.
Good. Okay, so photoelectric effect is one of those. When you get to the quantum physics portion of the course, there's only a couple of things that we tried to exposure to, if you like, and they were these ideas that we've taught you a big pile of classical physics up to this point, and then you say, but hang on, there's a whole branch of physics, atomic, nuclear, modern physics, call it what you like, that is predicated on the idea that classical physics can't explain it. So when you get to the atomic physics thing, the only couple of things that we wanted to expose you to was this idea that waves, what we've traditionally thought of as waves, so electromagnetic radiation and those sorts of things, can sometimes behave like particles. And the flip side of that is that particles, under the appropriate conditions, can exhibit a wave-like behaviour. Okay, but principally, we wanted you to be aware of this idea that electromagnetic radiation, when it behaves like particles, has this sort of quantization property that says that the energy of the individual photons is related to the wavelength and the frequency, if you like, by the expression, Planck's expression that says that the energy is h times the frequency, and here we've written it as sort of hc on lambda, because if you don't get given the frequency, h times the frequency becomes, well, hang on, you've told me the wavelength, I can work out what the frequency is, because all electromagnetic radiation moves at the speed of light, so hc on lambda is the same expression as hf. So that's the energy of the individual photons when you're sort of looking at a situation where electromagnetic radiation is interacting in such a fashion that the individual photons are the, if you like, the model you need to adopt to explain that interaction. Okay. So in this particular case, it says you have a beam of monochromatic light incident on a metal surface whose work function is 2.05 electron volts. Okay, so energy is expressed in electron volts because energy in SI units like joules are vanishingly small, okay, because you're looking at an interaction between an electron, okay, so the electron volt is the more appropriate energy unit. And so what we're saying here is that you have to be given the information in such a fashion that you can apply an equation to the system, because essentially what you know is, you know precisely how much energy the individual photons have, because once you know their frequency or their wavelength you can work it out. When they interact with something, all of that energy has to be conserved, okay? And the only time you can easily determine the equation of conservation of energy is when the work function is all the electron has to do to escape the metal surface. Okay, so what it's saying here is, if you have a photon whose energy is greater than 2.05 electron volts, then an electron in the surface of the material can absorb that photon and then have the same amount of energy to do something, and 2.05 electron volts of that will be used to overcome the work function, and then the rest will appear as kinetic energy. Okay, but the maximum value of kinetic energy only occurs when it only has to overcome the work function. So if it's more tightly bound than a surface electron, so it's further into the material or something like that, it can still get ejected, but it'll have less energy than the maximum value of kinetic energy. Okay, so what this thing says is, the work function is 2.05 electron volts and the stopping potential is 1 volt. Okay, so what that essentially means is, when the light strikes the surface and ejects the electron, the surface has to end up positively charged, right, because you've taken an electron off it. So originally it was electrically neutral, now it's got to be positively charged. And the electron that's been ejected is attracted back to the positively charged surface. Now, if the potential difference is small enough, then it'll still get away. But as the surface becomes more and more positively charged, it gets harder and harder for the electron to get away. Okay? So the 1 volt is when all of the kinetic energy that the electron has is still not enough to escape. And if you wanted a sort of a gravitational equivalent, it's like trying to throw something off the Earth's surface. So you have to give it enough kinetic energy for it to overcome the gravitational attraction. And obviously it's physically impossible for a person to throw something off the Earth's surface, but you know that if you stick a rocket there and you give it enough kinetic energy, or the potential to do it, to convert enough kinetic energy, it can escape the Earth's gravitational potential and get away. Yeah, and that's what this is trying to do. It's just that the attractive potential, if you like, is appreciably smaller. So provided the electron can overcome the stopping voltage of 1 volt, and when an electron moves through a potential difference of 1 volt, it does an amount of work 1 electron volt, because that's how much charge is on the electron. Okay, so the work done is QV, the charge times the potential difference. So what it's saying is, the beam of monochromatic light must have photons whose energy is 2.05 to overcome the work function, plus 1, because the 1 volt represents 1 electron volt of electrical potential energy. So altogether 3.05. Okay, and then once you've worked out what 3.05 electron volts of energy, you think, okay, so what does the wavelength have to be? Because we know that a photon's energy is given by h times the frequency, or h times c on lambda, and then it's just a case of sticking in the numbers. Okay. But what we said, as a sort of something that you can keep in the back of your mind, if you like, because often people, if they make a mistake in this calculation, they make a mistake and it ends up being orders of magnitude wrong because they've divided by 1.6 by 10 to the minus 19 instead of multiplied by, or something like that. Visible radiation, which is where we sort of tend to focus our questions, if you like, or in the vicinity of visible radiation, from 400, which is the blue end of the spectrum, through to 700, which is the long wavelength or low energy end of the spectrum, right? Those wavelengths, 400 to 700 nanometers, correspond to energies of about 3.1 to about 1.7, 1.8 electron volts. So if you've got a wavelength between, or an energy between 3.1 and 1.8, you've got to be somewhere between 400 and 700. So if you do your calculation and you're not there, you think, well, I've done something wrong here. Yeah. Okay. So this was 3.05, and you sort of think, well, at about 400, it's about 3.1. It's got to be well at the blue end of the spectrum. So you do your calculation, you look at this answer and you think, right, there's only two answers that are possible here. Right? And if I don't get one of them, I've done something wrong, I'll redo the calculation, see if I can work out where I went wrong. So the other thing we have suggested to people, if you have trouble working your way through the solutions in the forward direction, right, then you can always try and come at it from the other direction. So in other words, you know how much energy the photon has to have, and you've got a range of answers here, and only about two of them look like they're vaguely possible. So you just quickly calculate the energy for those two wavelengths and see which one lines up with the 3.05. Right? Just in case you take a term from one side of the equation to the other and you forget to include the minus sign or whatever. Okay? So there's a couple of approaches you can take, and just, make sure that you've tried and to convince yourself that you've got the right answer. Because the way these questions are often written, there's often a distractor answer in there. So if you do something, relatively simple but wrong, you can get an answer, because most of the time you sort of do something, you look and you go, beauty, there's an answer, I've got the answer spot on. So that must be the right answer. But sometimes there's an answer in there that is the distractor for the people who do something, simple but wrong. They'll get that answer. Yeah. So there's some value in sort of working both directions from that perspective. Okay.
If you try to find the wavelength there and you're using work in terms of EV, so you do need to change that to joules, don't you?
Yeah, you have to. So that's right. So once you get to the, so when we say E equals HF, that will produce the energy in joules. But if you want to work with an expression that produces the energy in electron volts, then you just write E equals HF divided by the charge on the electron, and then it'll be in electron volts.
It won't change your wavelength value.
But if you did if you write HC on lambda E, yeah, it'll just give you the wavelength working from energy in electron volts. Yeah. It'll give you it in SI units of meters, so it'll come up as 10 to the minus 9. Yeah.
I'm still not getting that answer.
40? No? So what are you getting? 384. Okay. So the expression down the bottom of the... so this part here, let me just check. You're happy enough with this bit, right? That the 3.05 electron volts has to be the photon energy, because it have to overcome the work. So this looks like the 2.05, which is the work function, phi or W, plus the kinetic energy, and the maximum value of kinetic energy is equal to the charge on the electron times the potential difference V, QV. Because you sort of think, if I do work on something and it gets a certain amount of kinetic energy, and from an electrical potential point of view, by definition the potential difference is the work done divided by the charge in moving it from one position to another. So this looks like that, and this is 1 volt, and you don't have to put in 1.6 by 10 to the minus 19. You just sort of think, oh, 1 volt is 1 electron volt when it's the charge of 1 electron. So that's where the 3.05 comes from. And then what we're saying is, well, we know the photon energy, it's Planck's constant times the frequency, but we want a wavelength, so we're going to use Planck's constant times the speed of the wave divided by the wavelength of the wave, because for all waves, frequency times wavelength equals velocity. Doesn't matter, what sort of a wave it is. You sort of say the velocity is the wave moves one wavelength in one period. So the wavelength divided by the period gives me the velocity, and 1 on the period is the frequency. So this always applies. So all we're saying here is, well, if we don't know f, but we want but we've got a lambda value, we could write F equals velocity divided by lambda. Move it up that way, okay? And then, in this case, it's an electromagnetic wave, so the velocity is the speed of light. So this becomes c on lambda, okay? Now, this is in electron volts, so you have to convert it to joules to use that expression like that, okay? So if I go to here, it would look like 3.05 by 1.6 by 10 to the minus 19. That will be now the total energy of the photon in joules, and that should equal the Planck's constant, 6.63 by 10 to the minus 34, times c, which is 3 by 10 to the 8, that's the speed at which electromagnetic waves move in air, and then lambda. So the only bit you don't know is this bit here, so you have to sort of lambda equals 6.63 by 10 to the minus 34 times 3 by 10 to the 8 divided by 1.6 times 3 is 3 times 1.6 is 4.8, so I'm going to say that's about 5 by 10 to the minus 19. Okay, and 3 times 6.6 is 19.8, say it's 20. This looks like about 20 by 10 to the 8, and minus 34 is minus 26 over 5 by 10 to the minus 19, and that looks like about 4 by 10 to the minus 7 by the time you take the 19 up, so 400 by 10 to the minus 9. So if you did it more accurately, sort of you'd end up hopefully with the 4.07, and what'd you get this time?
Yeah, I got questions on that. On the formula sheet,
Yeah.
it has 6.626.
Yeah.
I'm using that, and that's what I was using.
Yeah. It shouldn't give you enough of a difference. It shouldn't give you that much difference. It's
Yeah.
6.63.
It's 1.3 different that value instead. I got 405.7 instead of 4.
Right. Okay. Yeah. 6.63 is 3 significant figures rather than 4. So yeah, I could see it sort of changing it by, maybe a gnat's whisker, but like you say, 1.5 in 400 is about 0.4%, right? So, yeah.
on the optic stuff, I think like
34?
34.
Okay. Okay, so it says the near point of a far-sighted person is 75 centimetres. What power reading glasses are required so that the person could read a newspaper held at 25 centimetres from the eye? Assume the distance between the glasses and the eye is negligible. Okay, so it's basically a situation where you're sort of assuming that this person's near point is 75 centimetres. Okay, so what that means is they can't see anything inside of 75 centimetres, but they want to put the paper at 25 centimetres. Okay, so what does the lens have to do to make this thing work? That way? Yeah. So what does before you try and do the problem, what does the lens have to do to make it work? Concave. So what it's trying to do is physically make optically make the object appear like it's at 75 centimetres. So it's effectively got to sort of throw it out there so that then he can, make it look like it's out there. So in other words, if you did a ray diagram for this, you sort of think this thing here comes through here, produces rays that are. So where's the focal point of this lens? We don't really know yet. Okay, and we don't know whether it's like that or like this. But essentially, what it's got to do is make the rays that this object is creating feel like they're coming from an object that's further away. Okay, so. What's the easiest way to draw that with a diagram? Let's say the focal point was out here, okay? And if you wanted to draw a ray diagram, you'd sort of think that the rays from the top of the object, if they come through let's assume it's a converging lens, okay? Came through a converging lens, the one that came in parallel would be refracted and refracted as it went through the lens, so that it would pass through the focal point on the other side. Okay, so the focal point, that ray would end up doing that. Okay, and then the ray that would have passed through the focal point on this side, so the ray that did this, say, and went through the top of the object, so that these two rays are emanating effectively from the same point on the object. Okay, when it came through this lens, it would come like that. Okay, because if it comes through the focal point on one side, it goes parallel on the other. If it comes in parallel on that side, it goes through the focal point on the other side. So these two rays, your eye says, okay, now it looks to me like those two rays came from back here somewhere, and they came from the top of the object. So that's what the lens is trying to do. It's trying to change the path of the rays, so because your eye sort of sees, if the lens wasn't there, it would see these two rays diverging, and it thinks, I can't focus those two there, right? I can't work out I can't see in that close to my eye, so I need it pushed out so that I can focus it on an image out there. Okay, so that's essentially what the system looks like. It's a converging lens, and that's what it's trying to produce. It's trying to take an object at 25 and produce an image at 75. Okay, so then you can try and use the lens equation. Okay, so the lens equation is the same for all of these systems. So it's 1 on the object distance plus 1 on the image distance, and some books write it as 1 on O plus 1 on I, others write it as 1 on DO plus 1 on DI, and others use U's and V's, whatever, equals 1 on F. Okay, so it's the sum of the reciprocals. Now you don't really need to, know how to derive that expression. It's basically just a bit of trigonometry from the diagram itself, but it's on the formula sheet. So the only thing you have to be careful of now is that you know the sign of the terms. So the object distance is virtually always going to be a positive number in a real system like this, because the object's on the left-hand side of the lens. Okay, and then the image distance is a positive number when it's a real image, and a negative number when it's a virtual image. So this is like a virtual image because the rays of light that your eye is focusing to form the image, they don't really pass through that image. The rays of light are starting here and coming through the lens, but your eye makes it look like they started somewhere over there. Okay, so generally if the image is on the same side of the lens as the object, then it's a virtual image and it should be a negative number. So in this case we sort of say, oh well, the object's at 25, and the same thing applies here. Because this is 1 on D0, 1 on DI, 1 on F, as long as all those D0, DI, Fs are in the same units, you don't have to go to SI units. So 1 on 25 plus, I want this to be at 75, 1 on 75, but it's minus 75 because it's on the wrong side of the lens, equals 1 on F. Okay, so if you do the put this over a common denominator before you, okay, this looks like 1 on 25 is 3 on 75, just multiply top and bottom by 3, minus 1 on 75, okay, equals 1 on F, probably off the screen by now, okay, and 3 minus 1 is 2, so 2 on 75 equals 1 on F, so invert the equation, F equals 75 divided by 2, 37.5 centimetres. That's the focal length of the lens. Okay. Now, the answers are given in powers, so they're given in diopters. The power of the lens, P, is equal to 1 on the focal length in metres. Okay. So if I convert that to metres, it looks like 0.375 metres. And 1 on 0.375, okay, well if it was 1 on 0.4 it would be 2.25, okay, so it's obviously bigger than that, and when you do the numbers it should come out as, okay, 2.7, and it should be positive because the focal length is positive, yeah, it's a converging lens, not a diverging lens. Yeah. But yeah, for most of these questions, I think it's one of those things where you can do it just using the formula and hoping that everything works out right. But if you do a sort of a ray diagram, even if it's, like questionable as to how close to scale it is, at least you get a feel for what the answer should be. Yeah.
From there, sorry, how do you get to the answer?
To the D value?
Yes.
Yeah, this is the last bit here. The power of the lens,
Yes.
is 1 on the focal length. And our focal length was 37.5 centimetres, but once you do the power of the lens, you do need to express the focal length in metres.
Yeah.
So the 0.375, so 1 on 0.375 should be the 2.7 number.
We just need to know that because that's not on the sheet.
I'd be surprised if this wasn't there, 1 on F. I didn't print off that formula sheet for that evening. Olivia, can I have a quick look at this, just to see whether it is there? That's okay. I can get it from here, I reckon.
You've got resolving power on that for the microscope.
No, it's not there. Oh, I had yeah, that should probably be there. No, it's not there. What I was going to say was, when it's, generally speaking, if it's one of those situations where you think, do we need to have another formula here? If we don't notice it beforehand, so we can correct it on the paper, we generally correct it at the venue itself. So if people come up with a question, even if it's during the exam and think, do I need to know something else to do this question, then just ask the invigilators. They'll normally say to the sort of unit coordinator, hey, come on down, and someone's got a question here. And yeah, if you didn't remember it, you'd be stuck there. So yeah, it should be on there, the power of the lens expression. Let's see if we can do the reverse. There we go.
Can you go through question 24?
24. Okay, yep. So, capacitors are really just devices for storing charge. So, and generally speaking, we sort of model them like this. So basically just parallel plate capacitors, if you like, two bits of metal that are relatively close together. And essentially what you do when you connect these guys to a battery, okay, so let's say we imagine that we connected this to a source of EMF or a battery, would look something like that, and conventional current for a battery flows from the high potential side to the low potential side. Electron current, if you like, goes in the reverse direction. So the influence of that battery would be to take electrons off that plate and charge it positive, and put those electrons on this plate and charge it negative. Okay, so when you charge up a capacitor, you store electrical energy, but you store a finite amount of electrical energy. So when you involve a circuit with a battery, you imagine that the battery will just keep driving the current as long as the circuit's connected. Whereas if you charge it with a charged up capacitor, as soon as the capacitor discharges, it's used up all its energy. So in a lot of systems where you want to deliver a sort of a finite sized amount of electrical energy, the easy way to do it is with a capacitor, because then you don't have to think about disconnecting the circuit. So heart pacemakers and those sorts of things are basically just little capacitors, and they charge up and then they discharge and then they charge up again and then they discharge, so you can sort of produce a particular size voltage spike at a rate, whatever rate you want, by having the charging cycle have a particular amount of time to charge up, discharge. Okay, and other devices that use finite amounts of energy in the same process are things like indicators on cars and, you know, flashlights on cameras. You basically charge them up and then you discharge them quickly, get a bright flash of light and it goes out. Okay, so heart defibrillators are a similar sort of thing, except that for heart defibrillators, what you really want is a pretty large voltage, and it's not easy to cart around a large voltage supply that produces voltage continually. Okay, because in this case they're trying to produce a defibrillator voltage spike of about 50,000 or 5,000 volts. Okay, because in order to get sort of, I mean, a heart pacemaker, you don't need a very big voltage spike to make a heart pulse. Okay, because most of our bioelectrical pulses are pretty small voltages, but that's the voltage that you have to apply to the membrane of the heart. And if you're going to try and do it by sticking a voltage up here on the person's chest, you need a fairly large voltage for the heart to experience the right size voltage to kick it into gear. Okay, so yeah, one of the consequences is you need to carry these defibrillators, which are essentially just charged up capacitors, and then you can charge them up to 5,000 volts. You don't have to worry about trying to do it from your 12-volt battery in your car, because you can't really charge it up to any more than you can charge up the voltage you're using. Okay, so it's a system that's been charged up to 5,000 volts. Okay, but it'll only, you know, store a relatively small amount of charge and discharge for a very short period of time. So you don't have to worry about sort of electrifying the person, because it just sort of all happens and it's done. Whereas if you stuck 5,000 volts of potential difference on them from a voltage supply, they'd get it until you took them off it. Right. So that's the mechanism. So essentially all we're trying to do is work out how much energy is stored in the charged up capacitor, and the energy is essentially 1/2 the capacitance squared capacitance times the voltage squared, 1/2 CV squared. So when we did kinetic energy, we said you see expressions of this sort of form for a lot of energies. Okay, so for kinetic energy we had 1/2 mv squared. Okay, and for spring potential energy, if you like, 1/2 k or x squared, where x is the amount you displace it. If it was an inductor rather than a capacitor, so that it stored its energy in the electric field lines, energy stored in the magnetic field or the current would be 1/2 Li squared. And so there's that sort of 1/2 bar comes about a lot of times, because it's nearly always done by working out how much work you do to charge the device. Okay, so for the capacitor, Q equals CV. Okay, that's how much potential difference exists once you put a certain amount of charge on it. So if you start off with a flat capacitor, no charge on it, and you try to take an electron from this plate around to that plate, how much work do you have to do? Right? When the device is uncharged, you don't have to do any work at all, because you're trying to take it off a surface which is uncharged, so there's no force of attraction to that surface, and then you're trying to put it onto a surface which is uncharged, so there's no force of repulsion at that end either. So it's pretty easy. But then the more you do it, the harder it gets, because you're trying to take an electron off a surface which now is already charged positive and it doesn't want to go, and then you're trying to push it onto a surface which is already negative charged and it doesn't want to go. Okay? But if the voltage is big enough, it'll keep doing it until it gets to a point where it says, no, the amount of work that this voltage can do on that bit of charge is exactly equal and opposite to the amount of work that the capacitor wants to do to stop that charge happening. So it charges up and then it gets to a certain value and stops. Okay? But basically that diagram looks like that, right? This is a plot of sort of charge versus voltage, okay? And that would be slope C. Right, Q equals CV. So the work done, the total work done, is the area under this graph. Yep, sorry. And that's why these expressions keep coming up, because they nearly always end up looking like that. Because when you work out the force on a spring, it's the spring constant times the displacement. Okay? And the momentum for the kinetic energy expression, they all come about in exactly the same way. Okay? So the area of the triangle is a half the base, which in this case is the voltage you got up to, times the height, which is the charge on the thing, but the equation is given by that, so the charge on it is C times V. So it's times CV, a half the base times the height. Okay. So in this case, we just told you, you've got 5,000 volts, okay, and you've got a capacitance C, which is 24 microfarads. Okay, so the other thing we said during the lectures was that, and this applies sort of to a certain extent in the EV sort of notation for the atomic physics things, SI units aren't necessarily the most appropriate units in a lot of interactions, but they're in order to make all the units sort of work across the whole range of physics, you have to adopt SI units for everything. But then you inevitably end up having, you know, these sort of compromises, and one of them is this idea that because we have a sort of a unit of current being an amp, but we know that the current that's flowing is made up of a whole lot of electrons, and an amp is so many coulombs, you know, it's 1 coulomb per second, but one electron is 1.6 by 10 to the minus 19 coulombs, you end up having vast numbers of electrons, and the same thing applies when you get into the capacitance domain. You end up having these sort of micro, pico, nano type capacitances all the time. So it's just a consequence of SI units that capacitances are nearly always 10 to the minus 6, 10 to the minus 9, 10 to the minus 12 of a farad. Okay? But all you have to do here is sort of say a half times the voltage, which is 5,000 squared, because it's a half CV squared, times 24 times 10 to the minus 6, and then take a half of it. Okay? And that's where the 300 ends up coming from, because it's like 25 times 24, which is 600, half it is 300, and then just get the, you know, order of magnitude right. So there's 10 to the 3 here, and there's 10 to the minus 6 over here, but this is 10 to the 3 squared. Okay, so it's 25 times 24 divided by 2. And the orders of magnitude sort themselves out. Yeah. So even though it looks like a pretty high voltage in the normal sense of voltage that we're used to, because there's not a lot of charge stored there in a microfarad capacitor, there's not a lot of energy involved. Number 15. Let me find him first. Okay, over there. Right. So essentially what the system looks like is something like this. Okay, so three materials are being considered for thermal insulation. The thicknesses and the thermal conductivity of the materials are given by the following table. So if you have an object that's experiencing a temperature difference, okay, so in other words it's sort of T cold on one side and T hot on the other for the purpose of the exercise, what direction is the heat going to flow? Which way are we? Top to top, sorry. I need to draw something on the board here so I know roughly where the... I had a purple pen but I mustn't have brought it with me. Okay, that's around about the top of the screen. So, which direction is the heat going to flow? Yeah, the zeroth law of thermodynamics says heat will always flow from the hot side to the cold side, okay? And it'll only flow when there's a temperature difference. So there's got to be a temperature difference and then it'll try and flow from the hot to the cold side. So what governs how fast it flows? The rate at which it flows. No. The specific heat will influence the rate at which the temperature changes once the heat gets there, right? Because it's sort of, specific heat says, if you give me this much heat and my specific heat is this much, my temperature will go up by this much as a consequence of that amount of energy. Yeah. Okay. So no, what governs how much heat flows is the thermal conductivity . And it's another one of those things where we've sort of drastically shorter letters, so we use K again. So the thermal conductivity K, okay, and then that's of the material itself, okay, and then if this was thicker, right, for the same temperature difference, the temperature gradient would be less, if you like. So if I made it sort of 10 degrees temperature difference, but I put it really close together, then there's a large thermal gradient. But if I had 10 degrees and it's over this much, then it barely notices that it's 10 degrees warmer over here. Okay, so the length governs how quickly it flows. So it's basically the temperature difference divided by the length over which it has to flow. Okay, and then the other thing that's important is the cross-sectional area. Okay, so if you have a cold surface and you just sort of touch it like that, you get a certain amount of heat flowing into the tip of your finger, but if you put your hand down you get an area that's commensurate with the area involved. Okay, so the more heat flows depending on the area. So the rate at which the heat flows, let's write it like delta Q. The amount of heat that flows in time T depends on the temperature difference, okay, so TH minus TC divided by the length times the bigger the cross-sectional area, the more will happen, okay, and the thermal conductivity. So if it's, you know, got a low thermal conductivity, a piece of wood, and I stick it in a fire, the end of the rod doesn't get hot for a long time. But if I stick a piece of metal in there and hold on to the other end, it's not long before you're feeling the heat. Okay, so it's times the thermal conductivity. Okay, so hopefully that formula is on the notes. But Ka temperature. So in this particular case, it's sort of saying to you, look, let's ignore this bit because it's going to be the same for all of the different devices. A certain temperature outside, certain temperature inside, which one works better to keep the heat out or the warmth in, depending on which way the temperature gradient is. Okay, so and again, the same thing applies, if you like, to the cross-sectional area, because for a given situation, you've got a temperature difference and you're going to stick a certain insulation there. The only thing that's varying here is the thermal conductivity of the materials and the thickness of the materials. Okay, so essentially all you're supposed to work out here is K divided by L will tell you how high the QDT is. Okay, so if you're trying to, so it says here, which material would be the best thermal insulator? What does that mean about K on L? Because this equation corresponds to thermal conductivity. So if I look at K on L values, when they're high, it's good at conducting. If I want it to be an insulator, I want it to be low. Okay, so you either look at K on L and try and find it to be low, or you look at L over K, the length divided by the thing, and look for that to be high, right? Because thermal insulation is just the reverse of thermal conductivity. Okay, so all you're supposed to do here is say, you know, one or other of those. So in this particular case, we've worked out the R values, which is the sort of standard notation for insulation. Okay, L on K. So this number divided by this number. Okay, so that would be 2/5, 0.4. This would be 4 on 3, which is 1.3, or this would be 6 on 2 if I just get rid of the .0s for each case. So it would be 3. Okay, so the best thermal insulator would be the 3, so material number 3. Okay, then the next would be material number 2, and then material number 1 if we wanted you to rank them. Yep. But yeah, it's this expression, but basically we simplified it down to just a L on K thing, because ultimately that's the only bit, they're the only two variables that are changing here. Let me have a squiz here. 27. Yeah. So, so the only thing, there's a couple of notational things here that you sort of need to be aware of. So, when you can see the X's on the page, what's it mean from the magnetic field point of view? Yeah, so the magnetic field lines are vertically downwards and you're seeing the back of the arrows because the points of the arrows are going. So your magnetic field is into the page, and then the other thing you're told here is that it's a negative charge. Okay, so the magnitude of the force, and in this case it would be exactly given by that expression, is QVB times the sine of the angle between the various vectors that are responsible here. So in other words, the velocity and the magnetic field bit. But in this case, they're all mutually orthogonal, so the sine of the angle is sine of 90, which is 1. Okay, so yeah, like you say, it's a right-hand rule as long as you remember how to enforce it. So when you do the right-hand rule, you sort of think, okay, so I'm going to have the direction of the magnetic field being the fingers and the velocity being that and the thumb being the, or whatever, okay? So there's a couple of different ways of interpreting it. The other way to do it is, when it's a negative charge, you can take the velocity and just use your left hand. Okay, so the magnetic field lines are my fingers and they're down into the board. So if I use my left hand, I'd say my fingers are down into the board because they're the magnetic field. My thumb is the velocity vector, so it's that way, and the palm is the direction of the force, so that's that way. Okay. If you did it for the right hand rule, you'd still have your fingers downwards because the magnetic field is downwards, and you'd say, but hang on, my thumb is the direction of the velocity, except it's an electron, so the current is really this way, and then it'd still be that way. Okay. So as long as you remember to, the direction of your thumb is effectively the direction of the current. Yeah, so in that case it's the QV put together. So the current, conventional current, is in the opposite direction in that case. So yeah, you can use the right hand rule or the left hand rule because it's a negative charge and you should get the same answer. But yeah, you should expect that what's going to happen is the force is perpendicular to the velocity vector, and that means that the force doesn't do any change to velocity from a magnitude point of view, but it redirects it. So when we say it's to the right, what we mean is that this guy here will do that. He'll just turn around, do a half circle and come out somewhere. And then the radius of the half circle is a function of the amount of charge, the velocity, and the magnetic field strength and the mass. So mass spectroscopy uses this sort of system to separate out elements which have atoms with different masses depending on their isotropic mix. Yeah. But yeah, it'll just do a circle and come back out.
We do 30.
30? No, fine, 30. Okay. '30 sort of sounds like it's going to be the induced EMF question, the change in magnetic flux. Okay, and you would get the right answer from doing the change in magnetic flux. You work out how fast the plane's going, so what area does it sweep out. Magnetic flux is the magnetic field density, B, times the area, A, and it'll give you the number, effectively the number of flux lines. So what happens is that if you sort of imagine taking a loop of conductor in a magnetic field and you move it in such a way that you change the magnetic flux, then it induces a current that produces a magnetic field that opposes the change and all those sorts of things. But in this particular case that can't really happen because you sort of imagine that because of the way the plane's moving, what's going to happen is that it's changing its magnetic flux. It wants to try and drive a current, but in trying to drive a current down one side of the instrument, you get a charge of one polarity on one wingtip and the charge of the opposite polarity on the other wingtip, and that looks like an electric field. And eventually, the electric field that you produce by separating out the charges will produce a force that's exactly the same size as the magnetic force, and then the charged particles will stop moving. Okay, so it turns out you get exactly the same value irrespective of how you do it. But this is sort of an example of motional EMF rather than electromagnetic induction, but you can get the same answer either way. Okay, so you can do the expression that we've done here where we said the magnetic force is the Q times the velocity times the B value, and the Q is just, in this case, the electron, because it's a metal sheet, so that's the charge carrier. So, and it doesn't really matter because the Q is on both sides of the force. So this is essentially like an equilibrium expression for force. So what it's saying is the electric force, which will be, as the charge accumulates on one tip and the opposite charge accumulates on the other tip, if you like, the electron will think, I want to get to the positive end of the wingtip, right? Because I'm attracted to that, and I don't want to go to the negative end because I'm repelled by the negative charge. Okay, but the magnetic force is saying to it to go the other way. I want you electrons all over that side, and that'll leave positive charge at the other end. And so you get to a point where the electric force that's sort of saying, I want to go back there because that's positively charged, and the magnetic force which is saying, no, go in that direction, are equal and opposite, and that's when it stops. Okay, so the electric force is given by this expression here, that it's the charge on the particle times the electric field strength, and the electric field strength is the potential difference divided by the length over which that potential difference exists. Okay, so you can express your electric field in either newtons per coulomb, or you can express it in volts per metre. Okay, so we're going to express it in volts per metre, and we're saying the potential difference between the tips of the wing divided by the length of the wing times the charge, which we're not going to put in because it's going to cancel out because it's on both sides, should equal the magnetic force, and that's when the charge will stop flowing. And so when the plane first flies into the Earth's magnetic field, there's no charge on either wingtip, and then charge starts to separate, it produces a potential difference, and when the electric force balances, the magnetic force stops producing any more potential difference. It sort of says, no, we've got to the maximum value we can get here. So QE should equal QVB. Okay, and you end up just saying, oh, okay, but E is V divided by L, the potential difference. So there's two V's here. Should try and make it more obvious. This little v is the velocity, this capital V is potential difference. Okay, and L is the length of the wing span. Okay, but once you get to this expression here, get rid of the Q because it's on both sides. The potential difference equals V, B, and it was divided by L on this side, so multiplied by L on the other side. Okay, and then you whack in the numbers. All the numbers are given for you up here. It's got a 50 metre wingspan. The magnetic field density is 5  by 10 to the minus 5 Tesla, and the plane is moving with a velocity of 720 kilometres per hour, which you have to convert to metres per second. So everything's in SI units. Okay, so the magnetic field is given to you in SI units, the wingspan is given to you in SI units, but the velocity is given to you in, sort of conventional units of kilometres per hour. Convert that to metres per second. Multiply it all together and you end up with a potential difference in volts. Now, if you had have done it from the magnetic flux perspective, you would have said, let me get rid of that right here. The induced EMF should equal minus the change in magnetic flux with time. Okay, and you end up saying, but hang on, the magnetic flux phi B is the magnetic field strength times the area. Okay, so this starts to look like minus B. I still have to do the change in area over change in time. Okay, so what's the change in the area, if you like? Well, it's the area that's being swept out is the velocity times the length. Because if, you know, you sort of have a pen of a certain, say here's my plane wingspan, if you like, the amount of area I'm going to sweep out in the next second is that length there times how far I move. So the VT bit is the length of the area and the wingspan is the other. Okay, so that's where the BLV expression comes from. Okay, so this expression here looks exactly the same as the force equivalence expression that we had before. So you can do it either way. You can either say, from a magnetic flux perspective, what's the area that's being swept out in the time, and multiply it by B to get magnetic flux. Change in magnetic flux equals induced EMF. Okay, or you do it like we've sort of written a solution for it, where you sort of say, oh, it'll develop a potential difference, and the potential difference will stop increasing once the electric force balances the magnetic force. Okay, so that the charged particles in the conductor that the plane's constructed out of will sort of experience a force, and they'll move until the force is balanced. Okay. So the only complication after that is converting the velocity term from kilometres per hour into metres per second to get the expression correct.
It's 42.
42. Yeah, okay. So 42 says that we've got sort of radioactivity due to carbon-14 measured in a sample of wooden casket from an ancient burial site was found to produce 40 counts per minute, whereas the same amount of carbon from a sample of living wood produced 160 counts per minute. What is the age of the casket? So the idea is that the... Hey?
I was just looking at it.
Yeah. So essentially the argument is that when the casket was made, its carbon-14 to carbon-12 ratio should have produced the same number that air currently does today. So that quantity of wood locks up a certain number of carbon atoms, and in the process, some of those carbon atoms will be carbon-14, and that amount of wood, you work out how many carbon atoms there are, and then you say, so the number of carbon-14s will be this much, so the radioactivity should be this much. And rather than go through that exercise, if you happen to take a similar chunk of wood produced today, it would have a count rate of about 160. Okay, and then you say, right, so that bit of wood that's in the casket, however many years ago was producing 160, now it's only producing 40, so in one half-life it would have gone from 160 to 80, in two half-lives it would have gone from 80 to 40. Oh, so it's two half-lives old. Yeah, so that's 2 times the 5,000 number. Yeah. There's sort of, this is a reasonable assumption, this idea that the 14 to 12 abundance won't have changed that much in that period of time. But if you sort of have, if you go back far enough, you start thinking, but hang on, do we need to correct for the change in the, like, we know what the current abundance ratio is. Maybe a long time back, the 14 to 12 ratio was different. Yeah, but if it's short enough time frame, you can go, no, it won't have changed that much. Yeah, so a lot of these questions you can sort of go through and do them using the actual formula that involves the half-life or the probability decay constant, but a lot of the times you can just do it by, get to the right answer just by saying, oh, okay, so how many half-lives do I have to go to get to the right range? Yeah, rather than do the sort of inversion of the logarithmic equation or the exponential equation. Question 9. Yep. Yeah, okay, so this is another one of those questions which is sort of an application of the centripetal force type expression. Okay, so basically two satellites are moving in the same circular orbit around the Earth. So we're having to use the universal gravitational expression to work out the force, because it's not like, you know, generally if you're on the Earth's surface and you're trying to work out the force on a mass, you say it's mg, little m times g, or the mass of the object times little g. But this expression here is the correct expression. Okay, and what happens is, if you're near the Earth's surface, then the universal gravitational constant, capital G, times the mass of the Earth, which is about 6 by 10 to the 24 kilograms, divided by the distance between the centres of mass, which is effectively the radius of the Earth's spherical shape, they all combine to produce little g. So instead of using that expression all the time, you think, hang on, just make g me on the radius of the Earth squared equal to 9.8 and we're sweet, mg. Right? So that's how we normally do it. But once you get away from the Earth's surface, you have to use this expression. Okay, so all this equation is saying, look, if you've got an object and it's orbiting the Earth, a satellite, then the reason why it's orbiting at a certain radius is because the centripetal force required to make it orbit at that radius is exactly equal to the gravitational force of attraction. And that's how we put objects into orbit. You sort of go up there and then you say, right now I'm at the right altitude, and if I give you this velocity, you'll just keep going around. So I can either have a polar orbiting satellite or I can have a geostationary satellite. If I go far enough away from the Earth's surface and I put a satellite above a point on the equator and I say, if you go this fast, you'll take 1 day to go round the Earth, and in that time the Earth will do one rotation, so you'll always be looking at the same bit of the Earth. Okay, so that's essentially what we're doing all the time with regard to locating satellites. So those two terms have to be equal. The centripetal force, mv squared on r, that's the force required to make it go round and round in a circle, because the satellite doesn't care that the Earth's spinning. It just thinks, you weigh this much, I'm attracted in that direction, but I'm moving in this direction. So it's a bit like the problem we looked at before with the charged particle going through the magnetic field. The force is inwards, but I'm moving that way, so I go round a circle because I'm always going inwards, but I never leave the circle, sort of thing. So that's exactly what happens here. So you just say, oh well, you know, compare the two expressions. Okay, so mv squared on r, g me ms on r squared. The mass of the satellite is on both sides of the equation, so it goes out. So once you know the location that you want the satellite to be, it doesn't matter how much it weighs. So it doesn't matter if its mass changes along the way. It should stay at the same altitude, okay? Because the gravitational force varies at exactly the same proportion to the centripetal force for the mass, okay? So you end up with the idea that the velocity squared for the satellite is just given by the universal gravitational constant, which isn't changing, the mass of the Earth, which isn't changing, the radius of the Earth, which isn't changing. Okay. So two satellites are moving in a same circular orbit around the Earth. Mass of the satellite A is twice the mass of satellite B. Makes no difference because it doesn't depend on the satellite mass. Compare the speed of the two satellites. Okay. So the speed should be exactly the same, because the speed at which they move, which is the v squared bit, okay, well the square root of that, but the v is just made up of, right, if they orbit the same object, so the mass of the Earth, g, and the radius to where they are, and they're in the same radius, they'll go at the same speed. But again, it's sort of an aspect of that uniform circular motion and gravitational stuff that we probably didn't do in anywhere near as much detail. There's a pile of applications, and really if you try and you end up going through too much material, then people never get any sort of conceptual understanding. They just see another example and think, oh, here we go again, something else to learn. Yeah.
Question 8, which formula are we using for that?
Okay, so a child slides from the top of a frictionless slide. The height of the slide from the ground is 5 point. What is the maximum speed of the child when it reaches the bottom of the slide? So what is the idea here is, because it's frictionless, okay, there's nothing, no term to take energy out of the system. So the object just accelerates under gravity. So it converts its gravitational potential energy to kinetic energy. So that's all this expression here is, right? Conservation of energy says that the gravitational potential energy plus the kinetic energy should be, am I on the right bit? Yeah. So mgh is gravitational potential energy, and a half mv squared is kinetic energy. And what we're saying there is effectively we're taking, because we're measuring height from the bottom, at this point EP equals 0, because h equals 0. At this point EP equals mgh, but the person's not moving, so their kinetic energy equals 0. Then once they start to move, they move by virtue of the fact that they're getting closer to the Earth and giving up some of their gravitational potential energy. So just conservation of energy, essentially. And what it's saying is that the mass doesn't matter. So in other words, a small child or a large person, if there's no friction, they should get to the ground with the same velocity. So the velocity should just be the square root of 2gh when you do a little bit of manipulation of that expression. So yeah, if you have a slide, it shouldn't really matter. If there's no friction, it doesn't matter what the slide angle is. It'll take longer to get to the ground if it's flatter, but you'll get to the ground with the same velocity. Practically that doesn't really happen because there is some friction. So if you slide for longer, you lose more energy to friction, you get to the ground going slower. Yeah. But if you treat it like an ideal system and there's no friction, it shouldn't make any difference.
In terms of refraction, refracting towards the normal is refracting towards perpendicular.
Yeah, so the normal generally if you have a medium, an interface between two media, okay, so this is sort of medium 1 and this is medium 2 down here, then in order to work out what's going on, the first thing you have to do is draw the surface normal, the line that's perpendicular to the interface. Okay, and then if you have light coming in, you measure the angles relative to the normal. So this is theta incident, call it theta I. Then if it reflects, it goes out like that, and this should be theta R, but that should be equal to theta I, because if it's a specular reflection, it just comes, right? If it transmits, okay, and generally speaking, a little bit of both will happen. It just depends on how much different they are as to how much goes in and how much gets reflected, okay? But the bit that comes through, if it gets slowed down, it refracts towards the normal, and if it speeds up, it refracts away from the normal. So if you just drew that so that it came through perfectly, that would happen if there was no interface, right? So if the medium is, if the velocity is slower down here, it goes like that, and if the velocity is faster down here, it goes like that. Okay, so this is faster and this is slower, and then you know when you define the refractive index, n, which is our way of sort of dealing with changes in the medium, the refractive index is the speed in a vacuum divided by the speed in the medium. Yeah, okay, so that when you go into a new medium, you always slow down. Okay, so, well, relative to a vacuum, I mean. So this number will always be less than that number, so everything should have a refractive index greater than 1. Okay, now we tend to think of air as having a refractive index of 1, but if you sort of, you know, go to enough significant figures, the refractive index for air is something like 1.0003, right? So it's always going slower than the vacuum, but yeah, generally speaking, you don't notice changes in the direction of propagation unless there's a significant enough change in refractive index. So generally we're thinking, are you going from air to water, are you going from air to glass, or are you going from water to glass, and you're going from 1.1 to 1.3 or 1.3 to 1.5, or oil might have something else, but yeah. So yeah, if the n value increases, then you're going slower, so your angle decreases. And your angles are always measured relative to the surface normal. Yeah.
for question 35, are we given the refractive index for glass?
That sort of stuff I would expect would be in the useful information at the back of the page type of thing.
The data sheet.
Yeah, on the data sheet. So 35 you said, right? So it says, in the polarisation experiment with a slab of glass in air, the Brewster angle for air glass interface was found to be 50. When the slab of glass is placed under a liquid, the Brewster angle is, what is the refractive index? Yeah, so the expectation would be that N for the glass is probably, say, 1.52 or a number like that, but it'll be on the formula sheet of it, right? But because the two interactions are glasses involved in both of them, right? So it's like air glass, liquid glass. You don't need to know a glass value, yeah, because it's like what we did here was we sort of said, oh, when you work out the Brewster angle, it satisfies this equation here, that the tan of the Brewster angle is equal to N of the higher refractive index over N of the lower refractive index material. Okay, so it's like if you work back, it looks a little bit like Snell's law, except Snell's law says N sine theta 1 equals N sine theta 2. Okay, but we ended up with an equation here that said N tan of the angle instead of sine of the angle equals Ng on Na. Okay, and if you sort of look into that in a little bit more detail, it corresponds to the case where the angle between the reflected bit and the transmitted bit is 90 degrees. Okay, so that it turns out that the refracted angle is the composite angle of the incident angle. By that I mean that if the incident angle is 50 degrees, then the composite, to make it add up to 90, is 40. Okay, so you end up with N sine of 50 equals N sine of 40. But then you say, but hang on, sine of 40 is cos of 50. And then I can take the cos over the other side and it'll look like sine on cos, which is tan. Yeah, so that's where that equation comes from. But you get the Brewster angle is when you get that all the light that gets reflected is plane polarised, and for that to happen, the transmitted and reflected have to be orthogonal components, and then one polarisation will go one way and the other polarisation will go the other way. Yeah. Oh yeah, we didn't do that, but yeah, you just use the Brewster angle formula. But yeah, because glass is common to both, you can eliminate the glass value. Generally, I mean, occasionally questions will have things and you find yourself thinking, I need to know something, it'll be on the formula sheet, but often if it sort of sounds like, well, I probably should have been given the value because I don't know the glass value, and they give me, you know, the fact that glass has got a range of values depending on the style of glass, you think, okay, so maybe I don't need to know it, maybe it's going to cancel out in the algebra that flows through the solution. Yeah. And then, yeah, in this case, you sort of, almost intuitively, if you like, you should be thinking about, there's only probably two answers that work here, right? Because you sort of think, I know water's about 4 on 3, 1.3, I'm expecting an answer, it's either 1.3 or it's 1.36. If I don't get one of those two answers, I've done something wrong. Yeah. The flip side is, if you had have assumed an Ng value, you would have you could work it out if you wanted to, but you don't need to know it, because you're pretty safe in assuming that the Na value, the air value, is 1. Yeah.
Building 210, are we in the big theatre room in there?
That's where the exam is?
Yeah,
Yeah, that sounds like Elizabeth Jolly or,
yeah.
yeah.
Because there's two meetings.
Yeah, it should be 210, 101 or 102, depending on whether it's Elizabeth Jolly or, what's the other one, Norman Dusty or something? Yeah, I think it's the second one. Yeah. Okay, so like I said in the email that came out, if you do have questions that you don't think of here, you can always just send us an email or come and see us in the office, whatever. But,
When's that? Tuesday?
hey,
Tuesday.
I think you guys are Tuesday morning, 8:30. Yeah, yeah. There's that. Both the physics exams are on the Tuesday, so I've got guys Tuesday morning and Tuesday after. Yeah, you guys are the morning.